So hello everyone. Yeah, welcome to the Bitcoin Optech session, latest in Bitcoin tech. Uh, we will continue to discuss the quantum report that we started discussing last week. It's a voluminous report, and we covered half of it last week. I'll quickly go over what we covered last week. Just give an outline of it, and then move on to this week's content. If any of you like want have missed it, the last week's recordings are available in YouTube. You can always go have a look at it. So the report is sort of a status check or kind of where we stand, kind of report. So we discussed the last week we discussed the cryptographic foundations in Bitcoin, like what is a hash function, what is the ECDSA, signing algorithm, what are discrete lock problems, and how it protects our public-private key pairs, and what are all the threats to these cryptographic foundations from quantum compute. So we had a discussion about that. We had a detailed look at it. Uh, then we had a discussion about the state of quantum compute currently as it stands now. We had a brief discussion about what is physical qubit, what are logical qubits, where does Google's Willow stand now, where does Microsoft Majano stand now, and what is IBM doing, and what is its current status. So we had a brief discussion about that. Then we looked into the public key vulnerabilities. So, considering that elliptic curve discrete lock problem will be the one to be broken by quantum computers, we had a look at what types of public keys out there in the network are vulnerable and how vulnerable are they. We differentiated between two types of attacks: long range attacks and short range attacks. And we also had a look at the UTXO set, where do we stand now, which is the most predominantly used address type, and how vulnerable it is. Then we also looked at some of the practices that users do on chain that lend itself to quantum vulnerable attacks. So how do you spend it? How do you maintain your addresses? So all these things, the user's behavior basically on chain does impact the vulnerability also. So we had a discussion about that. Then we had a discussion about man in the middle attacks. So basically quantum, apart from quantum just posing threats to the foundations in Bitcoin, it also poses threats to the foundations of all tech, particularly in the internet. You can like they can break SSL. So this brings in a big threat vector, which is man in the middle attack. So the attacker can sit in between mining pool and the miner. The attacker can compromise or spoof the communication between the pool and the miner. So the attacker can also sit between hardware wallets firmware and the user itself. So in this way, quantum threats can also attack. Uh, like using this route also, quantum threats can be realized on the network. So we had a discussion about all these things. This week we will have a look at what quantum mining is and how much of a threat does it pose. Then we'll discuss into what are all the post quantum techs that we have right now in our hand, and at what stage of development these techs are all there. So we'll briefly have a look at it. Not a very detailed deep dive into what these things are, but we'll just have an intuitive, try to have an intuitive understanding of it, and then look at where these techs stand. Then we'll have a discussion about the moral dilemma that every Bitcoiner faces, provided the quantum threat is real, and it can be it can be like the provided the quantum threat can happen. So we face some moral dilemmas. So we'll have a look at what these moral dilemmas are. Then we'll have a look at the migration pathways. So there are different ideas or protocols that are proposed in order to handle the migration. So we'll look at how this might happen. Then we'll also have a look at the timelines that we are looking at uh, in order to make all these changes. So yeah, so that sums up, gives you an overview of what we'll try to cover today. Let's start with quantum mining. So quantum mining is all about applying quantum computers in order to break or solve much more efficiently uh, um, uh, the nonce. So basically, mining is a process of hashing a block's header repeatedly, so that you try to arrive at a hash value which is less than the nonce. So if your hash is less than the nonce, that means you have won a block. So this is the process. So the idea behind a quantum computer is to somehow come up with ways and means to do this hashing faster. So that's how a quantum miner can will work. Uh, it's an active area. It's an area of active research. Many research are going on the algorithm side, which type of algorithm to use, how to efficiently use it. But we'll also have to keep in mind the dynamic nature of mining here. So mining itself is very dynamic. So the hash rate keeps on increasing or decreasing. Recently, we had a very high hash rate crash, and we are looking at a significant difficulty adjustment in the coming days. So this hash rate is highly variable. The quantum miner, if at all is realized, has to be devised or has to be engineered in such a way that it can work in such an environment. And we should also keep in mind the ASIC hardware development that is happening parallel to the quantum miners. So ASICs are getting powerful by the day, and they are still a very valid, even with the quantum computers. ASICs are also very valid hashing instruments. So we have to keep that also in mind. Overall, all these things plays out in the arena of economic incentives. So we have to consider the cost of a quantum miner, and will it be able to mine at a cheaper rate than an normal ASIC would. So all these things go into defining the future of quantum mining. So having these things in mind, we can look at how a quantum miner can be used to attack Bitcoin's mining process. So
Bharat, curious if this is already at research and design stage, or is it only an idea right now?
this the algorithms are being continuously worked on and improved upon. So mainly the algorithm that is worked on is called as the Groover's algorithm. So what Groover's algorithm does is that it reduces the order of operations or time required in order to in order to perform a SHA-256 hash. So that's what a Groover's algorithm is. Groover's algorithm is designed for quantum computers. So the algorithms are being worked on, but in order to realize the algorithm, you need a significant amount of qubits that are available for the algorithm. So that part we have not yet reached some level of maturity or uh,
Got it. Got
certainty.
it.
So
And I think, yeah.
first to go will be your first easiest to attack will signatures, ECDSA signatures.
Yeah.
Only then can they move to the hash.
Right. And I think for mining and for hashing algorithms, quantum mining is a breakthrough in the right direction, right? It is not breaking SHA-256 because it's not based on, yeah.
Uh, it depends. You can use it to attack also. It will be a huge centralizing force on mining. So definitely there won't be any home miners who can run a quantum computer in their home to
Yeah.
mine. So even if it is used even if it is used for constructive purposes towards Bitcoin, it will be a huge centralizing
Yeah.
force.
Makes sense. Yep. Yep.
Yeah. So, from the perspective of an attack, what you can see is that when you bring a quantum miner to the hashing to the mining protocol of Bitcoin, you can use it to increase the rate of stale blocks that you can find in the network. So, basically, stale blocks are something like uh, you have this here I have shown an overview of a fork happening. So this is the chain that keeps on advancing, and you have a fork. So that means these two blocks are valid blocks that were found at the same time by two different miners. So now there is a fork in the chain, and these two miners propagate their block among the network, and whoever starts building on top of whichever block gets goes on to become the longest chain with highest proof of work, and this fork will get adopted, and this fork will be left behind, which means this block will be dropped. So this is how a fork works, and this block becomes a stale block. So because this miner has successfully propagated his block uh, to the network, and the network has started to mine on top of this block becomes a stale block. So this is an example of how a stale block is created. So with a quantum miner, what can happen is that because uh, uh, because like you can engineer a quantum miner to increase the number of stale blocks. So how this can happen is that uh, when a quantum miner starts to hash, it is not like a classical miner, wherein in a classical miner, the bits that the classical miner uses exist in either zero or one state. But in a quantum miner, it exists in like the probability. How can you can explain it as the idea is called superposition, which means at any given time the probability of your bit being 1 or 0, the the probability is there for your bit to be both 1 or 0. So that is the quantum superposition principle. uh, so how does it connect back to the mining is that, so whenever you give a hash, whenever you give a block header to the quantum miner, it will start to hash, and uh, at any given time, it in its probability space, the right answer for solving the block will always exist. So now what the algorithm does is that it will improve the odds of the quantum miner arriving at that particular hash, which is less than the nonce, which will enable the miner to solve it. So you can imagine it like some sort of a cloud, where inside the cloud all possible solutions exists, and the miner or the algorithm slowly sort of sorts through all the cloud of solution that exists out there to pick the right solution. So that's how a quantum algorithm works. So now when you put this, how can you use this to engineer stale blocks? So now as the miner keeps on trying to solve for the right solution so that it can win a block, while it is doing that, it gets or it becomes aware that some other miner has found the block. As a class, in the classical mining case, when this happens, the classical miner or ASIC just drops whatever computation that it had done so far. So it might have spent some energy and computation in order to search a solution for the current block. But because the block has already been found by somebody else, what it can do or it has to do is drop the entire work that it did and then move on to the next block. So otherwise, even if it continues and finds a right block, this block will become stale, since somebody else has found the block and somebody has already propagated the block throughout the network, and people would have started building upon the other block itself. So this is what happens in the classical case. But in the case of quantum miners, what you can do is that once you get to know that somebody else has found a block, you can just collapse the computation. So what happens when you collapse or abort the computation is that it's called as a wave function collapse. And once you close the algorithm, it's like shutting the door close. Once you shut the door close, you can imagine some sort of an envelope, or some sort of you can imagine it as some sort of an envelope slipping through the door. So when you open this envelope, there is a good chance that this envelope might contain the solution for your uh, for your block. So in the case of quantum computers, you either find a solution or you don't find in the case of classical ASICs, you either find a solution or you don't. So there is no intermediary state, or there is no probability of you finding a solution. It's an either or kind of a situation. But in the case of quantum compute, you might have spent some time trying to find the solution, and when you want to abandon it, you might get an output back that has a good probability of it being the actual solution. So that's how the weirdness of quantum computers come in here. So you can engineer your quantum miner to behave in such a way that whenever it receives information that there is some other miner that has solved the block, it can collapse its own computation that it has been doing so far, and then get a solution, and that solution has a good chance of being the actual solution for the block. So now what happens is that you get a state where there is two blocks, two valid blocks. So this can be a two valid blocks. So anyone can become a stale block. So either the quantum miner's block can become a stale block, or the other miner that found the block can be a stale block. So this is bad for the network, because if you keep on increasing the rate at which stale blocks occurs, there will be a lot of synchronization problems between peers. You have to have a lot of reorgs, quite frequent reorgs. So this, if potentially scaled up to a high degree, could destabilize the network. So this is an overview of how a miner can be used as a uh, threat threat vector. But realizing this in practical is not very easy, because there is likely to be wide performance gap between a quantum miner and a classical ASIC. So as you asked, Rayan, right now there is no quantum miner that is capable of meeting an ASIC's hash rate. So as of 2025, an ASIC could do 500 terahashes per second. Uh, but even in the optimistic scenarios, people have estimated that a good quantum miner can only reach 13.8 gigahashes per second. Um, and also, all this thing runs on Grover's algorithm, and parallelizing Grover's algorithm is not an easy job. And you need to spend a lot of resources in order to parallelize the Grover's algorithm and make it effective. So all these things has to make economic sense. So only then a quantum miner could be used to attack the network. So it was a mouthful, and I hope I was able to convey the idea behind the quantum mining attack. Okay, so now let's move on to the post quantum tech that is available with us. So this has evolved over a lot of years. It's not something new. So people have been working on post quantum stuff for a long time. It can be thought of sold as Satoshi himself. So basically, in the very early days itself, there were questions raised about or questions raised about our discussions that were happening about replacing the elliptic curve and also the SHA-256 hash. But the context of the discussion was not quantum when Satoshi was around, probably in 2010. It was more around like the probability of a hash collision. During that time, Satoshi's opinion was that SHA-256 is very strong, and he expressed that if at all there is any threat, we can, like in an orderly fashion, shift people or move to a new solution. So that was the earliest discussion about post quantum cryptography. Then came Lamport signatures. So now Lamport signatures are looked at as a important area or development which can help us migrate towards a post quantum Bitcoin protocol. So Lamport signatures are not new. They have been there from like 1979 or 77. So they are because they have been there for a long time. People have worked on it, tested it, broken it, returned proofs, a lot of proofs around it, and that is why it is widely regarded as a promising quantum resistant signature scheme that we can move on to. When you look at a lot of other solutions that is proposed, the important criteria that we have to keep in mind is that whatever signature scheme that we adopt, it should be very old and well tested. So there is no point in haphazardly shifting or moving the entire protocol into something new or untested, where there are unknown unknowns, where the threat vectors have not been fleshed out clearly. So that's why people are looking at Lamport signatures as a significant solution or important solution. Um, but there are a lot of problems with Lamport signatures. So as the development community has to come up with a lot of solutions to the problems that Lamport signatures have. Basically, Lamport signatures are one-time signature schemes. So, which means you have a public and private key. Once you create once you sign your transaction with your public key, it also reveals your private key. So, this is a big problem with Lamport signatures. The second problem with Lamport signatures is that its size is very huge. So it's typically 120 times the size of your ECDSA or SNOR signatures. Um, so these Lamport signatures are different from ECDSA because they belong to a class called as hash-based signatures. In a Lamport signatures, there is no curve involved. So as if you know about ECDSA, you know that you have the elliptic curve, and you pick points on the elliptic curve in order to first you pick a point on the elliptic curve, that will be your private key, and you derive the corresponding public key on the elliptic curve. So this is how you arrive at a public private key pair on your elliptic curve. But in Lamport signatures, there is no curve. So it's all based on hash. And as we saw last week, quantum computers are will hopefully be very good at breaking elliptic curves, but not hashes. So hashes are a lot more challenging for a quantum computer to break into. So that's why this Lamport signature scheme is being looked at or worked on as a potential for quantum resistant cryptography. Then there is another proposal to introduce an opcode called opcat in Bitcoin script. So this is there is actually a BIP in it, and there is already a BIP called BIP 347 that has been written to introduce opcat. So what is opcat? Opcat is an opcode that just concatenates two elements in a stack. As you all know, for a context. The Bitcoin scripting language is very strict or very limited in its nature. You can't do much in it. It's not a general programming language. You can do only very few things. It is Turing incomplete. You cannot have loops inside it. You can only have basic conditions inside it. Opcat is an opcode that can just concatenate two elements on the stack and then put the concatenated element back onto the stack. So this is what it does. But through some clever engineering of opcat and taproot, we can realize quantum resistance in the existing structure. So this is another proposal that is being discussed or uh, that is being discussed as a potential for post quantum systems on Bitcoin.
I think Opcat is also the. Yeah, sorry to interrupt you, but I think it's also the simplest. What I've read about it so far is it's the simplest opcode and proposal to also do governance, right?
Yeah, Opcat is more like it is simple because the changes that you have to make on the code base is very small. It is limited to like totally 15 lines of code on the code base itself. But it is powerful enough to realize a lot of other things. You can use Opcat to realize post quantum schemes on Bitcoin. You can use Opcat to realize covenants of different types on Bitcoin. So that's why
Okay.
it
Okay.
is promoted or it is being pushed by some people. It's not
Right.
new, something new. Opcat was there in Bitcoin from the very beginning, and Satoshi during the inflation bug one fine day he thought, okay, this is not good, and he just removed it from
So
the.
why does Jeremy Rubin talk about OpCTV being the most simplest opcode to do governance? I have.
Yeah, OpCTV is a very specific covenant. So it is basically used the idea behind CTV is that you have a template of actions that you can do with the script, which is already like you agree beforehand on what the template is, and you use that template while transacting or while executing the script. So there is no scope for anything new to come inside. For example, you can create a template to realize a vault, and this will be fixed. You cannot do anything more with the template except than to realize a vault. But in the case of Opcat, if this opcode is enabled, people can think. So basically, it's just a concatenation, and people can come up with any number of operations or some crazy ideas where they use the script to realize something which is really not intended to be on Bitcoin. So that is
Yeah.
the fear
Yeah.
behind
Right.
Opcat.
Yeah.
So
The
because it is,
argument against covenant is anyway more generic, right? That we don't know the unknown unknowns. Same goes for
yeah, yeah,
Opcat. Yeah.
yeah. So CTV is very specific in that sense. It can only be used to realize a few functions or a few type of covenants. It cannot be extended to all other crazy stuffs. Okay, so there is there is this another proposal called pay to quantum resistant hash. It's BIP 360. So it's a soft fork, proposed soft fork. So it what it does is that it introduces a new transaction structure with a dedicated attestation field. So this attestation field, you can use it to separate quantum resistant data from the traditional witness data. So so basically, when you serialize a transaction, these are all the things that goes into the serialization. Right now, you have the version number, then you have the marker, flag, inputs, outputs, witness, and finally log time. But this BIP 360 introduces a new attestation field before your log time, and you can realize all these post quantum algorithms using this attestation field. So that's a broad idea. So I don't want to go into the details of it. Uh,
Bala, do you think it's a coincidence that it is BIP 360?
uh, I don't know what is 360.
360 degrees? It's
360
a
degree.
circle.
Okay. I don't know. There is no logic to assigning BIP numbers, so that I know. It's up to the maintainer to assign BIP numbers. So there is no hard and fast rules as to there is no serial. So there is no serial order in which BIP's numbers are assigned. So it could be. I don't know. So so basically, BIP 360 will introduce an attestation field within which you can realize the post quantum algorithms. Within which you can realize the post quantum algorithms. So uh, there are a bunch of post quantum algorithms that are being debated or looked at. One is Sphinx Plus, Falcon 1024, Crystals, and your Lamport signatures is these algorithms are something similar to Lamport signatures. So this is a proposal that is currently live and that is being currently looked into by the community developer community. Then we have some other advanced proposals like Stark. So what is Stark? Stark is a scalable transparent argument of knowledge. So it's a zero knowledge protocol or zero knowledge proof system that is inherently quantum resistant, which means Stark does not use any elliptic curve ECDSA stuff. It just uses hashes, and it is built ground up to be quantum resistant. So how do we use this Stark in order to realize quantum resistance on the blockchain or Bitcoin blockchain? Is that you can use Stark to not reveal your signatures. So the problem right now is that when you sign and broadcast a transaction and it gets mined, your public key that you used while signing becomes part of the block and it gets exposed forever. And if you had used an address that is based on the same public key and you have some funds on that address, it will likely be broken open by a quantum computer. Um, this threat you can avoid by using Star, because if you introduce Star, it's a zero knowledge protocol. That means you don't have to actually reveal your public key while signing. Of course, it also requires some soft forks so that you can replace your signing algorithm with something that uses Star proofs. So this is one other idea that is being discussed, but it doesn't actually have much traction because of its complexity and changes.
But I like its acronym. It's so simplistic, right? It's
Yeah, yeah. It's simple. Yeah. So all these proposals are at various levels of discussion, various levels of implementation, various levels of adoption, like by the developer community at least. Um, so right now, BIP 360 is the most actively researched on or debated upon, and it is being most actively worked on. it probably, in my opinion, probably has a good chance of being adopted. Okay.
It's so amazing that we went from very technical discussion to a moral dilemma.
Yeah, yeah. So now, having said all these things, now we have whatever. Even though we have discussed a lot of tech, even though we can come up with a lot of post quantum solutions or tech, we have to face the moral dilemma that exists. So, what is it? If you see the category of bitcoins that are vulnerable to a quantum computer, it can be classified into three broad categories. One is Satoshi's coins. It is estimated that somewhere around 1 million of it lays around in blockchain. And there is an estimate of 2 to 3 million coins that are lost. People have lost their keys. And they exist in different address types: pay to public key, pay to public key hash, pay to public key segwit. They also exist in pay to pair multisigs. So this 2 to 3 million coins is a mixed bunch, and they are estimated to be lost because people have not moved them for a quite long time. So we have like 2 to 3 million here. Then we have like close to 6 million of coins which have their public key exposed, which means address reused stuffs. So people reuse addresses, exchanges reuse addresses, even though there has been constant education throughout the community as to not to reuse address. People keep doing it, and there is an estimated 6 million or so of coins that have their address reused. So the public keys in those things are all exposed. So so across these vectors now, as a community, we have to decide what do we do with these coins. So the options in front of us are, whatever protocol we adopt in a post quantum scenario, uh, two things can happen to these coins. You can either burn them, you burn them and then move on to a new, post quantum protocol, or you let the quantum computers come and steal them or claim them. So this is a dilemma that we have to, as a community, face and come up with a solution for. So there are arguments for burning it, and there are also arguments for stealing it, letting the quantum computers steal them. So if you look at the arguments for burning them, it it best preserves the integrity of the chain, and it helps you ensure the property rights. Yeah, so you basically drive home the fact that property rights on Bitcoin are inviolable. So that is there. But the problem is that when you let quantum computers redistribute Bitcoin that belong to someone else, it tantamounts to wealth redistribution. So, as a community, do we allow it to happen? That is another question. Then you have to treat the vulnerable funds as a protocol. uh, the history of Bitcoin and why it has been so successful is that it is a very conservative chain or conservative community or conservative ecosystem. Changes on Bitcoin are not very easy to come by, and it is very difficult to pull off any major change on the Bitcoin protocol. So many people see it as a bug or a feature. So many people see it as a feature of Bitcoin. So if you want to maintain that feature, we have to burn these coins. So that is one. That is another argument that is being made in favor of burning it. And also, in the post quantum world, there is going to be a lot of chaos and uncertainty. Burning sort of minimizes this chaos or uncertainty. So you can fix schedules for the burn, or you can pre-announce schedules for the burn and then
I
just
think
execute it.
yeah. I think one point I just popped in my mind is that it's more about coming to consensus. Well, right? That is its own chaos. Like developer community can't overnight say that hey, we are burning coins, right?
Yes. Yeah. We
Yeah.
can't say that. But the argument is that this is much better than the chaos of letting quantum compute
Yeah.
break open at their will. So this is the argument.
Yeah.
Okay. So basically, to reduce uncertainty and volatility, people advocate burning the vulnerable coins. As far as the steel argument goes, the argument is that when you burn, that is equivalent to confiscation of property. So you are basically you don't know whether the rightful owner is there or not, but you somehow assume that the rightful owner is not there, and you are reassigning, or you are seizing his property. So it is quite possible that the rightful owner is unaware of the threat, and he is unaware of the timeline, and so on. It is none of the developers or the community's right to burn their funds. So that is the argument that is being advocated in order to let the funds be and let it be taken away by quantum computes. And also there is some advantage with the steel option, because it basically equals to the do nothing thing. You don't have to break your head around the migration protocol that you have to adopt. You don't have to generate consensus. You don't have to rally the community or do anything. You just leave the protocol be as it. You introduce post quantum tech, and probably whoever is aware of the quantum threat and whoever is aware of the state of the network will move their coins from quantum vulnerable addresses to new quantum resistant addresses. Whoever remains will be picked off by quantum computes. So that is the argument for steel. With respect to the burn process, also there are a lot of intricacies. It's a big headache. You, as a community, we have to come to some consensus about what UTXOs we should burn, because whatever statistic we saw here is not hard and is not hard and certain. So these last coins, you never know. Somebody might be hodling it for so long, like they might be like seriously diamond handed guys. So you don't know, and you cannot just go about assuming that these are all lost and start breaking stuff here, start burning stuffs in this. Also Satoshi's coin, we never know. Satoshi might be around, he might might pop up someday, we don't know. So who are we to burn his coins? So these are all the questions that we have to address if we choose the burn path. And again, how do you disseminate this information if you are planning to burn? What is the best way to reach people? Somebody might be like Satoshi. I have moved on to other stuffs, and they might have tuned themselves off of all these stuffs. How do you disseminate information to them? And what is the appropriate transition period? Do we do it in a month? Do we do it in a year? Do we do it in 10 years? Do we do it in 20 years? We don't know. And how to implement burn process, that is also a big question mark. There is no agreed upon way to do the burn. Do we send them to if because we don't have the public keys of these addresses or private keys of these addresses, we can't create a new transaction. The only way is to engineer a hard fork and make new nodes not recognize these coins as valid transaction. So how do we do that? That is also a big question. And finally, what are all the legal implications? Somebody might come out one day and he might start a litigation as to who are you to burn these coins. So
But
these are all
who will he sue the What will the lawsuit be against? Is it the Bitcoin developer community?
Probably the developers. Yeah.
Right.
So here the argument will be that these are the people who implemented or enacted the burn process, and they are liable for it. So we don't know all these stuffs. So these are all the huge. The tech part is, I think, will be solved on its own. It will find its own way. But as a community, we have a storm ahead of us with respect to these things.
Yeah, by the way, this session is also the most science fiction session in the Bitshala's history. I'm pretty sure.
Yeah, just to add, there was one talk scheduled during the bid days, but I think due to some constraint, this talk didn't happen. It was around the quantum threat and the like roadmap ahead. I think the today's session covers all the aspects of that particular talk.
Yeah, correct. It was MSTR. He was earlier onto it, and he gave a nice presentation on the quantum, but it was fully like deep into the Grover's algorithm, Shar's algorithm, those kinds of stuff. Yeah, let's continue with the migration mechanisms that we have in our hand right now. It's all uh, work work being done, working on it. So nothing is final. These are all having to find a balance between network-wide enforcement. How how deep or how involved should the user be in the migration process, and what should be the implementation complexity? So these are all factors that are pull each other in opposite directions. So the process has to find some sort of a middle ground among these three factors. So that's the whole idea behind discussing different migration mechanisms. So these where do these trade-offs occur? These trade-offs occur from Bitcoin's inherent trade-off itself, which is we always try to balance between decentralization, sovereignty, and security. So these three trade-offs in migration arise from the fundamental trade-off that exists in the Bitcoin protocol itself. So what options do we have in front of us? We have something called as the commit delay reveal protocol. Very complex stuff, but it has some it is a complex implementation. It is more like it is more towards the let us like it gives enough time for the user to learn or understand this stuff and gradually migrate his stack to a post quantum protocol. Then we have QRAM. It is more of a cut and dry approach where you have a strict flag day, and then you say, okay, after this, all your coins are invalid if you don't move. Tough luck. So that kind of stuff, QRAM. Then we have an Argless strategy. This is particularly geared towards addressing quantum attacks that happen on transactions that are in mempool. Quantum vulnerable transactions that are in the mempool are also can also be attacked by quantum computers. So this Argless strategy is particularly designed or devised to handle that case. Then we have private transaction service, and then quantum canaries. So we'll have a look at these strategies in some level of detail. So the commit reveal protocol is the most complex among these things. So what you basically do is that you have three phases. One is a commitment phase, then you have a delay phase, and then you have a reveal phase. So in the commitment phase, what you do is that you pick your UTXOs that are vulnerable to quantum attacks. So you have any UTXOs, you pick them. So obviously, you will have a public key that you will use to sign for this UTXO. So you take that public key. You also will have to come up with a quantum resistant public key separately. So this CDR protocol assumes that the Bitcoin community has agreed upon a post quantum signature scheme like BIP 360 that we saw above, or Lamport signature, whatever it might be. The community has agreed upon the post quantum signature scheme. They have made all the soft forks for that particular change, and now they are ready to go. So in that situation, only after such changes have been made, you can come to this protocol. So it happens in stages. First, you have to introduce the quantum resistant tech into the protocol itself and get it ready, and then only you can start your migration. So this CDR protocol, you have the commitment phase where you put your public key and your quantum resistant public key. This means like now the protocol has made the necessary changes, and the quantum resistant key pairs are all agreed upon, and you can generate a quantum resistant public key like how you can generate a public key right now in your classical case. So now you are in that situation. In that situation, what you do is that you take the vulnerable UTXO's public key, you pair it with the quantum resistant public key, and then you hash it. Similarly, you perform a hash of all the UTXOs that you want to migrate. Then you put all these hashes in a commitment transaction. What is a commitment transaction? A commitment transaction is where you use a quantum secured UTXO as an input along with the outputs which contain op return data. Means you put this hash as a data into these outputs. So this is basically a commitment transaction. So now you have this transaction broadcast, and this transaction gets mined. After this, there is a delay phase. So there will be a mandatory delay phase of 6 months. You can't. So once this is broadcast, the network or the nodes will understand that you are these are all your UTXOs, and you are trying to migrate these UTXOs to a post quantum address. So what the network will do is that it will not allow anybody to spend these UTXOs just by producing the public key. Let's say you have broadcast this commitment transaction and it is mined. Now, if a quantum computer comes and it breaks your public key and it gets your private key and it tries to spend this UTXO, it can't, because you have already broadcasted this commitment transaction onto the network. So this is how this CDR will try to protect your UTXOs. So during the 6 month delay, you can't spend anything. You can't spend these UTXOs are forever locked for 6 months. So why do you need this delay? It protects you from adversarial chain reorganizations. It also makes it unfeasible to. Basically, the attacker might run or perform a 51% attack and keep building a parallel chain for long. But because of the 6 month delay, he cannot maintain an attack for so long. So that is the assumption on based on which the 6 month delay is proposed. So after this delay phase, then you have the reveal phase. So now you are once 6 months has elapsed, now you have the ability to migrate your vulnerable UTXOs to a new quantum resistant UTXO. So in this transaction, what you do? You put all your vulnerable UTXOs as an input, and you put the public key and the quantum resistant public key that you used for this UTXO as a as a witness. You also do an ECDSS signature of this input, and you also do a quantum resistant signature of this input and put all these stuffs into the witness segment, and you also reference this commitment transaction in your input. So when you do all these things, then you will be capable of sending this whole transaction or the reveal transaction onto the network. The network will mine it, and you will end up with a quantum resistant UTXO, which means all your UTXO 1, 2, 3, 4, 5, 6 till n will be converted into one single quantum resistant UTXO. So this is how the CDR this is how the CDR protocol has been designed, and it is quite complex, but it is sort of a middle ground between the quantum resist the it is sort of to the left of uh, QRAM protocol. QRAM is more like extreme or right wing kind of stuff. So what do we do in the QRAM is that you propose a flag day, and you say that after this flag day, if you don't migrate, all the UTXOs that are quantum vulnerable will become unspendable. So the advantage with that is that it is unambiguous. This CDR is very very ambiguous. You cannot expect people to move all their coins immediately. Some people will be aware, some people will not be aware. So that is a big issue. You have to take all those things into consideration. With respect to QRAM, that is you have a very clear timeline, or you can manage the movement or transfer. Then you have this R-glass strategy. So in this, this is used to protect attackers from from stealing your transaction that has been broadcasted and that lives in the mempool. So a quantum attacker can scan mempools, and they can claim the mempools transaction from the mempool. In order to prevent that, uh, sorry, that one was for the private transaction. So the R-glass strategy, sorry about that. The R-glass strategy is basically an idea to limit the number of quantum transactions that can be put inside a block. That means if an attacker, you have you basically have a list of addresses or UTXOs that are vulnerable to quantum attack. So you have that list. You make protocol changes in such a way that you can rate limit only one UTXO from this list can go into a block. So you rate limit the number of quantum vulnerable UTXOs that can go into the block. So this is basically designed to delay the attack, but not to prevent the attack. So that is an hourglass strategy. And then you have the private transaction service. So this is what is designed to prevent quantum attackers from stealing your transactions that live in the mempool. So in this strategy, you directly contact the miner. You don't have any you broadcast your transaction on the mempool. You directly contact the miner. You send him your transaction, and he just mines it. And you hope that the miner is not malicious. So that is the private transaction service. Then there is one other idea that is proposed for quantum canaries. So what are quantum canaries? I think you might have heard about the phrase canaries in the coal mine. So earlier, people used to send canaries into the coal mine in order to detect any poisonous gases are there or not. So that is the idea behind this one also. You basically spread or put bounties on the blockchain that are locked behind quantum solvable challenges. But these challenges are somewhat of a lesser complexity than that of your ECDSA or elliptic curve discrete log problem. So you put easier challenges across the blockchain, The idea is that if there is a quantum computer that is capable of solving it, it will try to solve it. By then, you can gauge and you can assess that a certain quantum computer of certain capability is now online and it is covering the blockchain and it can perform attacks on the blockchain. So this information is very necessary for us to calibrate our response to the threat. So people have proposed putting these things across the blockchain, probably as a transaction. So these are all the different migration pathways that are being discussed in the community right now. Uh, So apart from that, we have some idea about timelines. So the estimate is that if you run the numbers and based upon the industry's quantum computing industry's current projections, they project that they will be able to they will be able to double their compute. Means they will be able to double their logical qubits that they can create in 24 months, 18 to 24 months. That is what the industry quantum computing industry's projections are. So based on that projection, if we look at it, we probably have 10 years time, and by that time there is an expectation that quantum computers powerful enough to break the discrete log problem might come up. As of now, there is nothing like today, tomorrow, day after tomorrow. Nothing is in the horizon that can break the SEP 256 K1 curve. We are expecting it to be in 10 years, and that is also a big if. These all these things happens only if large quantum computing researchers like Google, Microsoft, IBM, they are able to keep up or increase the pace of investment on these technologies. So based on this, we have the report puts out some best cases and worst cases. Worst case, we'll have to wrap up our research and BIP writing within 4 years from now, and probably start implementing it from the fourth year. Probably worst case, we'll try to implement all the changes that we want by the seventh year. And migration is also a huge invariable or unpredictable stuff because based on our experience, it took almost 8 years since SegWit was introduced for migration to be effective. Like only after 8 years, we are able to see 85% of transactions that were SegWit based. So it took 8 years to come to 85% transaction based on SegWit. So based on this experience, migration, you can estimate migration to happen somewhere between 5 to 7 years. So that puts us like from now, it puts us like about 10 years closer to 10 years in the worst case uh, to migrate. So these are all the kind of timelines that the report discusses. Yeah, that's all I have from the report for this session.